Hello folks, and today I'd like to talk about stochastic feedback. And here on the screen we can see an example of Brownian motion. So this is particle which have quite random direction, and it can be 2D picture, 3D picture. The main idea, I think, is understandable. So why do we need to know stochastic feedback? In order to elucidate the notion of stochastic feedback, we consider a field, let's say we have speed of this particle. Oh, okay. Come on. Okay, v xt. So we consider a field v xt that describes the flow of a system. And for example, vxt may correspond to a component of a velocity vector field, and we then can assume that system variables, so this is our system variables, so this system variables change due to the flow of the system such that we obtain a linear transport equation. So let's write it down. So here we see d. So this is our system variables that are changed over time in a small amount of time, and you want to know how quickly it will change. So we write here t. So d psi I xt by t equals operator phi. This is our operator that depends on x, then number tv. Which we told before. Our psi, okay, our system parameters, system variables, psi xt plus r psi. So this is our equation. So as we said before, we assume that system variables psi xt change due to the flow of the system such that we obtain a linear transport equation. We can see it here. So d psi I xt by t equals operator f x number t depending on x number tv of system variables psi I xt plus ri. And here is a linear transport equation involving an operator. Here, operator. This is operator, right? If f depending on x number tv, that depends on v, okay, yeah, and some source terms ri. So we can say this our linear transport equation. Linear transport equation. So we say, you want to say, the origin, that the evolution of the field variables psi I xt is determined by the flow field vxt. So if vxt satisfies this equation, this linear transport equation, we deal with feedback. And in this case, this equation, which we can say that be equation number 5. So this is our equation, and this reads as follows. So we have a d vxt. Sorry, I will use vxt by dt. So we know to know how the velocity will change over time. In a small amount of time. And this is our operator, which depends on v and some other source terms ri. So t v plus r by v. Yeah? And in this case, this equation we can read as follows equation. We can say, okay, let it be equation number 6. And it is, and this case, as I said before, I wrote to it. This linear transport equation we can read like this: v d vxt by t equals f operator depending on v, t, etc. Number like plus r by v, and is nonlinear with respect to v. This is nonlinear with respect to v, and feedback of this kind equation can be found, for example, in hydrodynamics or hydrodynamic feedback. Let's found it here. Hydrodynamics feedback. Okay, we have some waves, some water just flowing like this, or some boat. in the ocean, like this. Very interesting, yeah. And exists some hydrodynamics feedback. If we consider laminar flows, so according to the first laws of physics, we know that what is laminar flows? It is like one direction. Laminar flow. Well, this is laminar flow. This is turbulent flow. So some different pieces of water can have in other directions, but we have laminar flow. It's in one direction altogether. And feedback of this kind equation, which I wrote here, can be found, for example, in hydrodynamics. And what else? If we consider laminar flows in the direction of the x coordinate of our brown particle, then v, which we wrote here, corresponds to the velocity and well, velocity field around velocity field vxt by x. So I can write it down also. Everything should be vxt by x of a fluid. So this is, so you consider laminar flow like this. If you consider laminar flows in flows in direction of the x coordinate, then the velocity field vxt by x of a fluid looks like this, and f operator f. Let's also write it down. We have also operator f. Is given by as okay, maybe I have a mistake. Okay. So, and the field variables psi, I, psi, those are field variables, correspond to the density field of the fluid and the temperature field and the velocity field vx vxt by x. And we can draw some of a picture which will help us to see the feedback of the system. So please. Okay, let it be here on the right side. So here we see laminar flows, and this is how it will look like. We have some many body system. Maybe I put some picture here. We have some many body system. And we have some conventional feedback. Also, we have to conventional, sorry, conventional feedback. And also we have maybe this a little. Let's do it on a bigger size. It's huge. It's huge. Many huge text. Place quickly. Load. Many body system. There are many body system. We can say it about. So this is our many body system. Also, we have some conventional feedback. We have stochastic feedback. This is also important. So a few moments and it will be done. This is our many body system. And here we have some kind of here. It's just take a so many body system. Maybe pen. Okay, we have many body system. We have uh, some conventional feedback on the system. X. We have conventional feedback and And we have a stochastic feedback. It is also important. Yeah. This is called stochastic feedback. So let us interpret probability density as some kind of flow. Probability density is some kind of flow, flow field V, and let us assume that the evolution of system variables, like this variables, is affected by the flow field pxt. Just let's write it down. We have pxt, right? And what else? So we want to interpret probability density P as some kind of flow field V, and we can say, let's assume that the evolution of system variables psi is affected by the flow field pxt in such a way that we obtain a linear evolution equation. So let's write it down. Let's be a little bit up. So let's write down our linear evolution equation. We talked about this. This is our linear evolution equation, or linear transport equation. We obtain the linear evolution equation for V equals P and Ri equals 0. So let's say V equals P and Ri equals 0. So, okay, now we can write our equation, new equation, and it will look like this. So, d psi I xt by dt equals operator f depending on x, no, or depending on p xt and some other parameters, some other source terms. Okay, x nabla t and pxt. And so here will be our psi I xt, some of our variables depending on x and t. See, this is our system variable depending on x and t. Okay. So what else? So this is our third equation, we can so this is the linear equation, but we say r equals 0, v equals b, and now we've got our 7 equation. And so if p satisfies its own evolution equation, that is v equals p xt, and if the operator f is given by now I have some logic. If some operator f depending on p and x and number t equals minus I, di depending on x, t, and p by dxi. Let's draw it here. It should work. By dxi plus okay, let's move it a little bit left. So plus ik some ik by d square depending on dik depending on xtp and all of this by dxi and dxk. This is our 7, our 8 equation. We know what our operator is about. Is equals our nonlinear formal equation. Looks the same like nonlinear Fourier equation, right? See it here. This is our nonlinear Fourier equation. This is our nonlinear Fourier equation. This is our nonlinear Fourier equation. And we can say 1.8. Right. Okay, now we have operator. Then, so we say two conditions. The first one, if P satisfies its own evolution equation, that is V equals Pxt, and if the operator F is given by this equation, right? Then we obtain the nonlinear Fokker-Plana equation, which we wrote here. Yeah, it's our nonlinear Fokker-Plana equation. What else? Consequently, we realize that this equation involves feedback as well. We will refer to this feedback as a stochastic or statistical feedback. Here we can see feedback, stochastic feedback. And in particular, as we will show later, for strongly nonlinear Fokker-Plana equations, the transport equation, this transport equation, in psi ixt, it is our variables for the system by dt, the changing by dt equals operator depending on x number t p xt on psi I xt, system variables. In particular, we'll see later. For strongly nonlinear Fokker-Plana equations, the transport equation applies not only for for psi for psi psi1 xt, but also for psi2 xt, depending on x derivative. But that is for transition probability density. That is for transition probability density. Okay, I will to sum up. For okay. This applies not only for psi1 pxt, but psi2 pxt, depending on x derivative to derivative. That is for transition probability density, and one may alternatively say that we can alternatively say a strongly nonlinear Fokker-Plana equations. The transport equation, this transport equation is f operator given by this equation holds for an infinitely large set of field variables psi1 equals pxt, psi2 equals pxt, depending on x derivative t, psi3 equals p xt, depending on xt, x derivative t derivative, x2 derivatives t derivative, and so on, that describe a stochastic process. Yeah, that's what we want to say. So like this and this. Let's throw it here. Maybe some derivative here. Yeah. So we can say that strongly nonlinear Fokker-Plan equations that strongly nonlinear Fokker-Plan equations, the transport equation, which we wrote here with given f operator holds for infinitely large set of field variables, psi1, psi2, psi3, and so on. And describe a stochastic process. It's very, very, very interesting and important to know. Yeah. By the way, if you want to know the basic features of stochastic feedback system, they are they can be illustrated on the diagram or on the figure that we draw here. So we have many body system which is totally formed. It can be human societies, it can be some fluids, pneumatic, some thermolytic stuff. And okay, in quantum mechanics, we have also examples of how some particles are going with each other, and there's some equation which is called heat. Okay, equation describe patterns and behaviors of this kind of systems. But it's only a sub-concept system, single. We need to know to describe behavior of whole system, which have inside a few subsystems together, and they interact with each other. And so many body system also have conventional feedback and stochastic feedback. And the basic features of stochastic feedback, system illustrated here. There is also should be a noise. We forgot about noise. Let's write it down here. Here we have a noise. We like noise. We don't do anything with that noise. Actually, we dislike noise, however, it is quite often used in our nature, so we have to know that noise exists. So it is here. This is noise, it's our many body system. And the noise has a little influence on our many body system. Yeah, and there is a noise source acting on the stochastic feedback. And what we can say also, well, there is two feedback loops, conventional feedback and stochastic feedback. And the conventional feedback loop involves the state variable x of a single representative subsystem. So we have a one subsystem, single representative subsystem is our state variable x. And the conventional feedback leads to transport equation. The form like which I will maybe draw somewhere here. Let's go right. So we want to know how our variables of our system changing over time. So we can write psi I equals 60. So changing over time by t, d psi I xt by t equals our operator f, depending on x, number and t. And multiply the system parameters psi I depending on x and t plus some plus Ri. This is our 9 equation. We can so the conventional feedback loop involves a state variable x on a singular representative subsystem, and conventional feedback leads to a transport equation, which we see here. And transport equation is formed like this. And in addition, there is a feedback loop that involves a subsystem density rho pxt, rho pxt. This is our probability. Oh, this is the density, yeah, density. And due to this second feedback loop, stochastic feedback, stochastic properties of the subsystem ensemble are fed back into the ensemble. So the stochastic feedback leads to transport equation also, such as oh, sorry, what is it? Some magic. Computer suddenly try to do some stochastic behavior on my laptop. Mouse became a little bit stochastic. So stochastic feedback leads to transport equations such as okay, psi xt by dt equals, oh sorry, here is a definitely should be derivative, I'm sorry. And here we also have the f operator derivative x depending on x, blah blah t, and our density multiply on our system variables psi I depending on xt plus Ri. And this is our maybe last the equation. So an equation, and if we use p equals rho divided on m, rho divided by m with with m0, with m0 defined such okay, let's say it again. If we use p equals rho divided by p is m0, with m0 defined such that p is a normalized unity. And can be cast into the form of this transport equation, linear transport equation. Yep, that's it. So we need to sum up what we understood. Now we know that what stochastic feedback is. So we have our manipulated system. It can be, as I said before, some inherent dynamics field, or it can be some society, some subsystems of society groups, subgroups, or maybe it can be just ferromagnetics or another system which have inside subsystems which are interacting with each other, and we have a conventional feedback and we have a stochastic feedback. We have a linear transport equation here, and we can state the notion of stochastic feedback. When we consider ext, it describes the whole system. So something like this. Now I want to hit it a bit. I think this section was quite comprehensive, and thank you very much for your attention. And okay, next time maybe we can see more examples, more applications where we use this nonlinear for Catalan equations, and maybe also we can do some experiments. Thank you very much, and bye-bye.